Today we are going to talk on a new topic, which is transformations, right. So, let us go back and revisit the rendering pipeline. So, if you recall, basically when we look at the rendering pipeline, we have the model generation stage, right, where different models can be combined together using what we call as modeling transformation, which are nothing but a sort of instantiation of these models, right, to build a three-dimensional world or a scene, right. So, we need some transformation which would take these models to build this 3D word scene, right. And then this three-dimensional word scene through a viewing transformation, right. So, viewing transformation, what it does is basically incorporates a viewer or a camera in the scene, right, and then with respect to that viewer, we generate that word, whatever has been constructed. So, after this viewing transformation, we again get a 3D scene, which is having a reference with respect to the camera, right. The point here to be noticed is that there is a transformation which is happening from here to here, right. And similarly, from this 3D view scene, we then project to come to a two-dimensional scene, right. So, that again requires a transformation, and then we may actually do the clipping, right, in that two-dimensional scene, or actually we can also do clipping in 3D scene, right. So, this projection box actually consists of doing the projection, that means reduction of the dimension, and also clipping, which gives us basically the 2D scene. And then through the process of rasterization, we convert this two-dimensional scene, which is device independent, right, to an image to be rendered on the screen of the monitor, right. So, this stage we have already sort of seen from the, we have seen the rasterization process, right. We have also seen some component of this projection, which is the clipping part, right. And now, what we are going to look at is the transformations which are happening in this entire pipeline, right. So, we notice that there are a number of transformations which can happen here. So, we start with a simpler scenario where we will look at these transformations as you are already perhaps conversed with the geometrical transformation, right, and we start these transformation in 2 dimensions, right. So, let us see what are the various transformation in 2D, which you are already aware and must have seen it in different contexts, are useful in the context of computer graphics, right. So, for instance, let us say the example of scaling. So, there is this point P having the coordinates x, y, which is transformed to P prime having the coordinates x prime, y prime after a scaling transformation, right. So, when I say there is a scaling transformation, then what I basically mean that this x prime is in the form of some scaling factor S x applied to x, right, and y prime is some scaling factor S y applied to y. That is what gives me the scaling, right. In other words, this transformation from x y to x prime y prime can also be represented in the form of a matrix, right, where I find the diagonal terms to be the scaling factors, right. So, I can actually represent this whole transformation in this form, right. There is a matrix here, which I let us say represent by S. then this P prime is nothing but P multiplied by this matrix S, right. So, if I have a figure like this, right, and let us say for the purpose of simplicity I assume that the center of this figure is actually at the origin, right, and if I perform scaling to this figure, is some sort of a contraction of that figure, I would obtain something like this, right. So, expansion and contraction, these are the kind of things we can obtain using scaling transformation. Now, the point which is to be noted here is that if I have the two scaling factors given by S x and x y to be the same, then I obtain uniform scaling, right. And if they happen to be different, then I have a non-uniform or differential scaling, right. And so this scaling is actually happening about the origin, in the sense that if I had this figure somewhere there, then you would have noticed not only the contraction, but also some sort of a shift, right, if I was doing scaling about the origin. So, here I have deliberately assumed that the center of this figure is actually at the origin, right. So, next transformation, let us see rotation, right. Here again we observe the transformation from P to P prime, right. So, here this point P is located, which is after a rotation about the origin. Again we are considering the rotation about the origin, it goes to P prime, right. That is what we want to look at, right. And let us say again there could be convention which would give me the rotation as a positive rotation when I go in counterclockwise direction, right. It is a matter of convention. So, let us consider these points to be in polar coordinate system, right, where I define this in terms of the radius as a distance from the origin and the angle, right. So, then I can represent x as r cos phi, y as r sin phi, right. Then the new point P prime after the transformation, having undergone a rotation by an angle theta, would be given by this r cos phi plus theta and y prime as r sin phi plus theta, right. So, this is all your high school stuff, right. There is nothing very new about it. So, then I can expand these terms, right, and substitute the term for r cos phi and r sin phi as x and y, and eventually get x prime and y prime in terms of only theta, right, terms involving theta and x y, right. So, once again I can write this transformed point x prime y prime as some sort of a matrix multiplication to the original point x y, right, and this matrix basically consists of cosine and sine terms, right. So, I am saying that P prime is basically P multiplied by a matrix which I call it as a rotational matrix for the angle theta, right. Okay. Now, let us go further and try to generalize this process of using matrix as a mechanism of performing transformation, right. So, we have basically seen that scaling and rotation could basically be represented as matrix, right. So, now if I take a point x going to x prime, where x prime is nothing but a multiplication of a matrix T, which I can consider to be a general matrix, general 2 by 2 matrix, right, having terms as A, B, C, D, right. then the transformed point is given by Ax plus Cy and Bx plus dy, right. And then it is actually the values of A, B, C, D which would define the type of transformation you want to achieve, right. So, for instance, if I just have A is equal to D is equal to 1 and B is equal to C is equal to 0, then I am basically constructing that matrix to be an identity matrix, therefore, nothing changes, right. So, everything boils down to something like a simple algebra using matrices, right. Now, so let us try to see that if I wanted to achieve scaling, right, then all I needed was basically only the diagonal terms, right, and the off diagonal terms are 0, meaning B and C are 0, right. Then I get scaling. And in fact, another type of reflection transformation which is reflection is actually a special case of scaling, right. So, there I am basically saying that off diagonal terms are 0, the diagonal terms are negative, one of them is negative 1, let us say, then I am getting a reflection with respect to one of the axes, right, and if both the terms are minus 1, then I am basically getting a reflection with respect to the origin, right. So, a point here, if I had both as minus 1 diagonal terms, then the point will come here somewhere, right. So, now basically we have figured out that this 2 by 2 general matrix can give us various types of transformation, right. Let us consider another example where I considered the off diagonal terms. The diagonal terms are 1, right, and the off diagonal terms are, let us say, non-zero. So, let us take one of the off diagonal term here. So, what I get is x transforming to x plus Cy and y is the same as previous y, right. So, what I get as a transformation is some sort of a shearing of the shape, right. So, by shearing I mean that there is a shape like this, right, it becomes like this, right. It is some sort of a skew stretching, right, and I call this as shearing in x because x is getting changed, right. Similarly, I can obtain shearing in y, right, where I would have the off diagonal term b to be some non-zero, right. Therefore, the y component is going to change as some function of x, right. Okay. So, this 2 by 2 matrix which we have considered gives us various types of transformation, right. Now, let us go further and see that if I want to actually perform a transformation which is translation. So, all of us understand what do we mean by translation, right. So, basically there is a point P which is displaced to a point P prime, right, with some offset displacement, right. So, if I have the point P x y which goes to P prime having the coordinates as x prime y prime, then what I am saying is that x prime is actually x plus some offset in x, right, which is given by T x, and y prime is y plus the offset displacement in y, which is given by T y, right. So, in other words, when I look at as an operation which is happening to the point P, I find that P prime is actually P plus T, where T is displacement vector, it is not the transformation matrix, it is just a displacement vector, and I achieve this p prime, right. Now, there is some kind of a problem here, because what I wanted to do basically, I wanted to capture all the transformations in the form of a matrix, right, which I could possibly do for many of the transformations, but not for translation, right. Here there is no such matrix multiplication which will give me a translation, right. So, now the question is, can I still be able to have a matrix representation incorporating translation? So, you understood what we are trying to achieve here? See, I wanted basically to achieve just as a matrix multiplication for any transformation I want. And what I observe here is that translation is basically the anomaly. It does not fit into that, right. So, now I want to devise a scheme by which I can still be able to do these transformations in the form of a matrix multiplication. So, for that what we do is we devise what we call as the homogeneous coordinates. Okay. Of course, there are other properties and characteristics of homogeneous coordinates, but one of the features which we want to use at this point is to have some sort of a unifying mechanism, right. So, let us say if I say the matrix multiplication which was happening for the transformation such as scaling, rotation, reflection, shearing as x prime is equal to x t, right, and the translation was happening as x prime is equal to x plus t. So, once again this t is different from that t, this is not a matrix, right. So, now what I do is I define the coordinates of p which were given as, let us say, two coordinates x and y with an additional coordinate which I call it as w, right. So, there is this p which is now being represented in homogeneous coordinates as x y w, right. So, there is this third coordinate which I have basically added, right. Now, with this I form a coordinate system where in fact I can have multiple values for the same point, right. So, for instance, the point with homogeneous coordinates as 2, 3, 6 and 4, 6, 12 are the same. Okay. So, geometrically, just to give you an interpretation of this, what actually is happening is that we have added now another coordinate to the point which is we call it as w, right. So, a point which was x y defined in a plane now has three coordinates x y w defined in a space given by x y and w, right. So, this is my point here. Now, if I consider the Cartesian coordinates, that is what we basically use for all our geometrical purposes, then it basically boils down to that I assign the value 1 to this w, which basically means that I divide x y w by this homogeneous coordinate w, and I get x by w, y by w and 1, right, which is nothing but a point on a plane w is equal to 1 corresponding to basically the line which is being formed by all the multiple value representation of the point, right. So, basically this is sort of being used as some sort of a scaling, the w part, right, and the all the points now form a ray or a line, right, and the value of w which I choose gives me the projection of that line onto the plane w is equal to whatever value I have, right. But for the purpose of our geometrical operations, or let us say the points which we represent in Cartesian coordinate system is given by when I have w is equal to 1, right. So, all these points basically which are on this line are the same points. It depends where I take the projection, right. Is this clear now? Okay. So, now having defined this as, let us say, a new system of coordinates for the points, let us try to investigate whether we can now unify the various transformations, right. Now, so basically the transformation matrix now what we are considering will go from 2 by 2 transformation matrix to 3 by 3 matrix, right, because now I have a definition of my points given by 3 coordinates with an additional homogeneous coordinate in it, right. So, once again if I look at the transformation which is happening to x prime through this transformation matrix T, where this x is now given as x, y and 1, right, that is where we define all the Cartesian coordinates, which in turn gives me x prime, y prime and w, right. And a matrix which I have here is a 3 by 3 matrix, right, where I have this part, the upper let us say portion of the matrix as the same as 2 by 2 matrix which I had earlier used, and there are these terms L and M, right, and deliberately I have put these 0 0 because the interpretation of those non-zero values we are discarding for the moment, right, but there could also be some other values here, right. So, a transformed point basically is given by this, right. Now, let us try to see whether we can derive the various transformations which we have seen through this. So, let us say if I had translation, right, if I had translation. So, translation would have basically mean that if I have the translation vector given by L and M, right, that is where I place the translation component to the matrix, right, and the rest of the matrix looks like this, then I am basically getting x prime and y prime values given as just the displaced values of x and y, which is x plus L and y plus M, right. Therefore, if I was just to perform the translation, this is how my 3 by 3 matrix would look like, right. Therefore, I can perform now the operation of translation as just a matrix multiplication, right. Similarly, if I was to perform let us say scaling or rotation or shear, this 2 by 2 general matrix which I had considered earlier, I would just place it there, and these there would not be any translation terms here, right. So, I put 0 0 here, right, and then again just the multiplication of this matrix T would give me the required transformation, right. So, we have basically devised a scheme by which we can obtain the transformation in terms of matrix multiplication, including translation. Okay. Now, let us say if I have to perform successive application of transformation, let us say we are considering one type of transformation, right. So, I am basically considering let us say successive translations, right. So, the first translation I defined as a translation as T1 given by L1 M1, the second translation I define as T2 given by L2 M2, right. Then what happens in terms of the matrices which I would apply for the two transformations? First, I will get let us say x prime, which is obtained after applying T1, the first translation, which is given by this matrix here, right, having the terms L1 and M1, and then I apply to whatever I get here, which is x prime, the second translation, which is given by this matrix containing the terms for L2 and M2, right, and which gives me the result as x double prime. Now, all I have to do is substitute what was x prime here, which basically gives me this matrix, right, and I just multiply the two matrices for the two transformations and I get this, right. So, there should be x here actually, right. So, this is just the transformation matrix which needs to be multiplied to x, right. So, x multiplied by this. So, what you observe here with respect to the transformation matrix or the transformation which is happening is that you have these terms here, which is L1 plus L2, and you have the term here M1 plus M2, which is now accounting for the two translations, right. So, which in turn says that translations are additive in nature with respect to what the transformation is happening, right. Now, let us say if I were to perform successive scaling, just the same thing again, right. So, here the scaling factors are given as x1 and sy1, and for the second scaling I have x2 and xy2, right. So, I just do the successive application of the transformation for each, and what I see here as the resulting transformation, which has the terms Sx1 multiplied by Sx2 and here Sy1 multiplied by Sy2. Therefore, I observe that successive scaling is multiplicative, right. Now, what happens if I do successive rotation? What happens? It is additive, that is right. So, that we can see it now here. So, I have a let us say rotation given by an angle theta, which I call it as r theta, and there is another rotation given by an angle phi, which I call it as r phi, right. So, after the first rotation, this is what will happen, right. After the second rotation, this is what will happen, right, and if I multiply these two again, this is the resulting transformation, right. So, this should be x double prime is equal to x multiplied by this matrix, right. So, this is the resulting matrix, this is not really x double prime. So, what we observe here is that rotations, successive application of rotations are additive in nature, right. You just add the angles by which they would be rotated, right. Okay. Now, so basically this was the first way to look at the composition of transformations which we were performing, right. So, there we were considering the same type of transformation, but there could be composition of different type of transformation which we need to perform, right. So, let us say now there is an example where I have a figure here, right. I know how to do the rotation about the origin, right. For that I have a matrix. But let us say the problem is modified and states that now you have to perform rotation about the point P, right. So, the question is, can I perform rotation about P using the transformations which I have just seen, right. So, since I know the rotation about origin, right. So, I have to just basically map my problem for rotation about origin, right. So, the best thing is to make this point P origin, right, perform the rotation and then do the post rectification, right. So, that is what here it stated the steps which one would need to do this rotation about P. So, the first thing which is to be done is that you translate this figure such that P becomes the origin O, you perform the rotation as you know the matrix for that, and then translate back to P, right. So, just to see what happens pictorially. So, this is what happens when we do the translation, right. So, this figure gets translated to this, right, and the necessary matrix which I would need is something like this, right. If I define this offset translation by L and M, right, then I am forming a matrix of translation given by this, right. So, these are minus L and minus M, right, and then I do the rotation about this origin, because I know what the transformation is, and this is the transformation I require for performing the rotation about origin, right. And then I take it back, for which I would need another translation, and the transformation of that translation would look like this, right. So, as a result, all I need to do is concatenate these transformations, right. Just do the concatenation of these transformations, which would give me the final transformation as this, right. So, again the x is missing here. So, this is the final transformation, right. So, that is a very big advantage here, using matrices as a representation of transformation, right. And that is what is actually used in most of the graphics library we have. Okay, now another example which would illustrate the composition of transformation. Let us say I want to perform reflection about this line which is shown here in the blue color, right, and this is the figure I have, right. So, so clearly I do not know reflection about an arbitrary line, right. I do not know the matrix for that, right. But again, by using the composition of various transformation, I can obtain that matrix, right. And what I know is, I know that if this line was one of the axes, right, if this line was one of the axes, I could do the reflection, right. This much I know. Therefore, I need to map this problem of reflecting about an arbitrary line to one of those, where I could do the reflection with respect to one of the axes. right. So, what do? We first basically translate the line, pass to the origin, rotate the line,
then perform the reflection,
right,
then we inverse rotate and
right,
then we back transform them.
perfect, right. So, you understand everything, good. So, let us see these steps. So, this is the translation which will basically make this line pass through the origin, right. This would do the alignment of the line with respect to one of the axes, and in this case x axis, right. This would do the necessary reflection with respect to the x axis or about x axis, right. And then we do the reverse things, right. We rotate it back and then we translate it back, right. So, this is the reflected figure now we have for the given figure here, right. So, just by using composition of transformation, we can actually enrich the class of transformation, right. Now, so when we are talking about this composition of transformation, there are words of warning, right. See, given let us say a transformation T1 and another transformation T2, in general I do not have the law of commutativity. It does not hold for matrix multiplication, right, they are not commutative. So, T1 T2 is not equal to T2 T1, it is, right. So, T1 T2 is not equal to T2 T1, right. So, but in certain cases it would hold, right. What are the cases?
So, if we perform the same transformation, like if we form two translations,
right,
then it will hold, or if we form two rotations, it will hold,
right.
In case of shearing as well, it will hold. Like if we perform same kind of transformation, this will hold,
right. So, if I have a two scalings, right, does not matter which one I do first, two translation does not matter which one I do first, rotations which one I do first, does not matter, right. So, they are commutative. But if I have let us say one rotation scaling, in certain cases it could, but not in all the cases, right, or translation rotations, right, they would not hold this, fine. So, one has to just be careful when we are doing these, when we are using transformation as matrices, then when you are trying to compose them, then one has to be careful. You can't just change the order of multiplication, right. Okay. So, now let us say the class of transformations which we are looking at, right. Just by seeing this matrix, we can actually obtain different class of transformations. So, for instance, rigid transformation are those transformations where shape is preserved, right, meaning I preserve the length and angles, right. Shape and size are basically preserved, that is what I mean by rigid transformation, right. So, square remains square. So, that I would obtain if the component transformations are of the type rotations and translations, right, which basically means that the 2 by 2 general matrix which I had considered A, B, C, D has to be the rotation matrix, right. Then I can also have translation here, which means that I have the terms for L and M, right. So this is how I can obtain the rigid transformations, right. The other class of transformation which are more general in nature are affine transformations, right. Affine transformations would basically mean that I have this general 2 by 2 matrix which I had used earlier plus translation, right. And what are the properties with respect to the shape it gives us? One thing is that it preserves parallelism, right. So, parallel lines remain parallel after the transformation, right. And the type of transformations which would give us the affine transformations basically would include rotation, translation, scaling, shear. So, all which is there as this 2 by 2 general matrix which we had considered plus the translation, right. And what is this 2 by 2 general matrix basically is actually linear transformation, right. See, if I have to disregard the homogeneous coordinate system, then x prime basically given as x multiplied by the general 2 by 2 matrix, let us say some A, right. And when I expand those terms, it becomes a linear combination of the terms, right, which is basically the linear transformation, right. So linear transformation is actually a subclass of affine transformation when I do not have translation, right. So, now if you want to see the difference here, in the case of linear transformation, the origin is going to map to origin, whereas in affine transformation this may not be the case because there is a translation, right. So, this class of transformation, affine transformations, are of particular interest when one is trying to do a change of coordinate system, right. See, I define, let us say, two axes x and y, right, and then I define another system of coordinate, right, where I have, instead of x and y, I have some other axes, right. So, using the affine transformation, I can actually map from one coordinate system to another coordinate system, right. So, the alignment of axis would basically be taken care by the linear transformations I have, right, and the shift of the origin will be taken care by the translation part, right. Okay. So, now instead of having these as 0 terms, I can very well have non-zero terms, and that makes a general 3 by 3 matrix for transformation. So, I basically have this 3 by 3 matrix where the last column now is changed to P Q S. So, instead of 1, I have now a term S, right, and instead of having 0 terms here, I have non-zero terms as P Q, right. So, let us say if I had this matrix where the diagonal term A D both were 1, these off diagonal terms were zeros, right, C L M and B P Q, and there was this S term other than 1, what would have you got? You got what I asked?
So the last quadrant would be S.
Yeah. So, this is other than 1 now, right. So far we have seen S equal to 1, right. Now, I am giving you S other than 1, and let us say, just to simplify the situation, the other terms are, let us say, off diagonal terms are 0, these are all 0, these are all 0, and A and D are both 1, right. So, what do you get? You got a scaling. Actually, what you get as a global scaling, right. Remember, there is this x, y, w, right, and while getting back to the Cartesian coordinate system, I would have to divide by this w. So, eventually the coordinates I have are x by w and y by w, right. So, in this case, this w will become s, right. So, I actually obtain a global scaling, right, and these p q terms are basically for the projective transformation, right. So, the projective transformation is a superclass of affine transformation, where lines map to lines, right, but parallelism may not hold, right. The parallel lines may not remain parallel after the projective transformation, right. So, this would make let us say have a better explanation and interpretation when we go to 3D transformations, okay, because that is where we will do lots of projection and so on, right. So, now in fact, having seen these 2D transformation, extending them to 3D is straightforward, right. All you have to do is, instead of using 3 by 3 matrix, now you use 4 by 4 matrix, right. Once again, we will work in homogeneous coordinate system, right. So, now there is an additional dimension z, right. So, we have point x, y, z, w, right. So, let us have the examples here. They are very straightforward things. So, if I have to perform scaling, now I actually can differentiate between local scaling and global scaling, right. So, here I am giving you the matrix for local scaling, right. Local means individual to each axis, right. So, S x, S y and S z are the respective scaling factors, and this last term is 1, right. Similarly, if I have to do now a rotation, right. So, there the rotation was basically about origin and implicitly about an axis which was perpendicular to the plane where that figure is, right. So, now when we talk about rotation in 3D, basically are going to talk about rotation about an individual axis, right. So, for instance, rotation about x axis would be this, right, which basically means that I am rotating about x axis, and I can again have a convention that if I use my, let us say, right hand system, right hand coordinate system, then the thumb is the axis about which I am rotating, then the rotation of these fingers, right, is giving me the positive rotation, right. So, that is what I mean by this is a positive rotation with respect to x axis, right. So, similarly, I can get, using this convention, rotation about y axis, right. So, this will be actually negative and this will be positive now. So, that is in line with my convention, right, and rotation about z axis, right, and so on. So, similarly, I can have translation matrix, right. So, where I have an additional term of n, right. So, it is a straightforward extension, nothing great about it. So, and the off diagonal terms will basically give me the shear, right. So, the whole transformations basically can be now represented as a general 4 by 4 matrix. So, it is a simple extension of general 3 by 3 matrix which I used in 2D, right. So, maybe just for the convention's sake, see, I have been using the points which are basically represented as a row vector, where I post multiply the row vector of my point, right. So, you can also use a column vector representation of the point, where you would pre multiply that, right. So, this is just a matter of convention. So, in some of the books you may find a switch, right, instead of using this post multiplication they will be using pre multiplication, but that is just a convention. Okay. So, let us stop here. We will talk more about these transformations and then we basically will go into the viewing transformation. So, these are basically class of geometrical transformation, right, where the geometry is modified, and then we also talk about the viewing transformation, right. Thank you.